Okay. Right. Let's get started. Dum, 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 dum. Okay. Welcome to second class. Today is your, I guess, your first real introduction to this interactive mathematics that I've been talking about last week. Not last week, 2 days ago, sorry. Okay. So some of you, I understand, haven't got the program or haven't got the laptop. So just find a friend, that you can trust with vaccination and whatnot. Okay. How many of you haven't got it with you? Okay, so not many. Okay, maybe you have. Okay, Cup. Very good. So last time I gave you a sort of like a prep talk of why it is that we need mathematical thinking, mathematical logic, and why it's going to really serve you well for the rest of your career. And it really doesn't matter which area, especially we're talking in reference to Basai's 4 area of specialization. Applied digital intelligence, obviously you're going to use a lot of mathematics, just the whole thing. But certainly with sustainable development track, with health science, and with smart cities, you'll be using tools, you'll be using visualization, you'll be trying to demonstrate your concept, apply your design thinking, and try to visualize. And a lot of it is really visualization of mathematics. Okay. Okay. Right. When I do this sign, I mean pipe down and pay attention. Okay. Hopefully, today will be the most boring class of this summer, because this is the mechanics kind of thing. Okay. Think of it as if you doing some kind of robotics, the first robotics lab, you're going to learn how to splice wire and how to, solder things together and so forth and make connection. Okay. And again, comment, by the way, next class, be very punctual. Okay. Being punctual is one of the easiest thing you can do, because nowadays everybody has a watch and a clock that sync. Okay. If you use your iPhone, your thing is linked by satellite. Everybody has the same time. There's absolutely no reason why anybody should be late. Okay. And well, you girls are not my daughter, but if you were my daughter, I would say, the first thing you check in a sign of a man is if he can keep time, because that's the easiest thing to do. If you can't manage to be punctual to time, he's not going to keep his word with everything else. So that's what I would say to you as my daughter, let's say. Okay, right. And bear in mind again, you guys are not monkeys in a zoo. You are human being in an institution. You sign up for this. So being punctual, being respectful, being quiet in class and all that, that's part of the human decency that you sign up to. And that's a condition for being a respectful student. Okay. And then we'll be more productive that way. Okay, there'll be occasion for you guys to discuss, and hopefully when I ask you guys to speak, you actually speak up. Okay, so I don't want you to be quiet the whole time. Right. Okay, so when we say mathematics, okay, and you hear this colloquially all the time, I'm not good with numbers, I don't like mathematics, I'm not good with numbers. You know what? Mathematics has nothing to do with numbers. Okay. Okay. Mathematics has nothing to do with number. It has mostly to do with relations. In fact, if you study mathematics as say undergraduate mathematics major, you would see kind of like 2 kinds of mathematician. Okay, this is just kind of a trivial. On the one side, a mathematician who are interested in things like function, how A relates to B and to C, and how you can model their relationship. Then there are groups of what they call number theorists. Now, these guys, they're also interested in relationship, but the object of their studies is actually particular numbers as well. So there is something about actual number, like prime numbers. They see number like 11 and they say, why is 11 a beautiful number, or 789 has a certain number theoretic implication, and they think it's a beautiful number. So they like number in that sense. Okay, but mathematicians, and in fact, mathematics is not about numbers. Sorry? Oh, I haven't shared screen. Sorry, my bad. Thank you. Okay, let's share the whole screen. Okay, can you guys see from the next room, right? Okay. Right. In fact, I myself, when I look at, say, economic reports and see a lot of tables with numbers, I get completely confused. I like to visualize my number in relationship. So I don't like tables of numbers. And so mathematical thinking is not about, being good accountants or very nitpicky about numbers. It's about relationship. So if I see a table of economic report, say from the Bank of Thailand, forecasting inflation, it's not the number. It's how the latest number stand in relation to the previous number or whatever, or the expectation and so forth. So you see, with things like, let's say inflation, right? Inflation. We don't talk about inflation as a number, but we talk about inflation in a frame of reference. Right now, headline inflation is so and so percentage. Let's say it's 3%. And 2.7 has been found to be consistent with a healthy, sustainable economic growth. Then you can say that 3 relative to 2.7 means the economy is heating up a little bit. Okay, it has a tendency to have too many investment activities, and it could, in 3 months' time, 6 months' time, lead to inflation, that sort of thing. Okay, so it could be inflationary pressure from, food price or gas price and so forth. So first of all, mathematics, it really is about relationship rather than about numbers. Okay. But we have to think about this. Certain things in life, and this I'm being a little bit poetic, if you have a mathematician's perspective, put on mathematician's hat, okay, and you just you take a walk down the streets, you observe things. What should happen is you would realize that certain entities, certain part of life is not quantifiable in numbers. Certain things are, a lot of things aren't, right? But in order, okay, and this is the name of the game, in order for you to do any kind of analysis, okay, just take my word for it. If you want to analyze, you have to put things in quote unquote mathematical framework. So everything has to somehow be translated into number or equivalent to a number, okay? And this is important. And it's not as restricted as you think, because you can talk about text, you can talk about picture. Eventually, through the modern marvels of AI, that I'm really very much into, all this, before it gets to the computer, somehow gets translated into numbers, into variables, into X, into Y. So just take my word for it for now, if you don't see the connection yet. But just imagine whatever you want to do in life, whatever object you want to touch, design, picture, language, meaning, ideas. If you want to do more than just storage, well, even if storage, you need to do it in math. But if you want to do some kind of analysis, okay, you have to turn into objects that you can analyze. And ultimately, it's all about turning things into X and Y and then manipulating those X and Y, right? So that's the marvel of modern data science. It used to be, when I was your age, okay, things like regression analysis. It's only applicable to certain data where you have quantitative numbers. all right? Some kind of modeling, some kind of prediction. It's only you working with something that inherently is numerical, okay? But nowadays you don't, right? When I take a picture of a cat on under an umbrella, okay? And I show it to my computer, and computer takes it and prints out the narrative in English, or it may be in Thai. I don't know if such program exists now, but certainly in English, a cat under umbrella. This is AI doing auto narrative, okay? You can bet that somehow the picture gets translated into numbers, and the output of the AI is a number before it gets to become a sentence, a cat under an umbrella. It's that, okay? But when I was your age, the possibility of doing something like this is very hard. Okay, you can do things like temperature today is, so many degrees Fahrenheit or Celsius, and yesterday so many degrees, and what's the prediction of tomorrow? So it's numbers to numbers to numbers, but not picture to sentence. Okay, but the power of mathematics is once you get into the form that it can play with, it can get very clever. Get very clever. Okay, so this is completely universal. Then, having said that, okay, and this is something that this is kind of like my interactive text. It's a text, but it's written in Mathematica. So every time you see an equation, you can activate it. Okay, I would save this probably into CDF, computable document format. So for those of you who doesn't have the full program, you can play along. Okay, right. Okay. So I guess what separate human beings, you can read along if you like, but okay. What makes us most competitive? What makes us more powerful than any form of sentient beings on Earth? Okay, we're not physically stronger than anybody, right? We're pretty much useless the moment we're born. But ultimately, the reason that we can conquer, well, not conquer, but at least manage our local environment and exert some kind of influence, good or bad, you have to admit human beings are powerful. And the key to humans' power is the power of abstraction. And abstraction, in so many words, it's about turning things you see into mathematics, in a loose sense of the word, doing some analysis on it, making prediction, and then map it back to reality. Okay? So it's your ability to perform abstraction and representation. Okay. Now, numbers. Let's think of number. Now, this is very, silly. You never had to think about number since you were a baby, right? But what does number do? Okay, there are actually two elements of numbers, and this is something that you don't realize. It does two things. One is counting, and one's measuring. Okay, counting, you can do something like a unit of this, unit of that, right? Well, measuring doesn't come automatically, but you can certainly count, right? How long is this room? 1 meter, 2 meter, 3 meter, right? And the reason you can count 1, 2, 3 meter is not because the room is inherently separated into a block of 1 meter. Okay, I can say 1 student, 2 student, 3 student, but 1, 2, 3 meters is completely artificial. It only happens when I have a scale, right? So that is one abstraction. Human being already beats the rest of the animals. I think if you go to like zoology lab, monkeys can count. Okay, monkeys can count how many bananas. What monkeys cannot count is banana length in inches, because the abstraction from the length into a meter, a scale, and then counting the scale, that's completely beyond any chimpanzee, as far as I know. Okay, maybe in the future that might be different. Okay, so right away, this is already a level of abstraction. What I like to tell you now is that precisely, this turning the length of banana into so many inches or so many centimeters, that principle is pretty much everything that modern data science and artificial intelligence, like I told you, ability to look at a picture and say it's a cat. At some point, there's that translation. There's that putting reality to scale. There's an element of measurement. Okay, so now let's get more concrete, right? Let's get more concrete. Certainly counting is based on identification. You can only count two things because you saw this one identity, right? And with measuring, you can do something like comparison, right? This banana is longer than that banana. Okay, fine. So that's basically it. The first thing you can appreciate being human beings is that abstraction. And you can think that you can take my word for now that the most advanced thing I do in data science and applied digital intelligence is nothing more than higher levels of abstraction. It's abstraction built on top of abstraction. It's function built on top of function. It's automation built on top of automation. Okay, so picking up a glass is basically a complicated task, right? But when you were a baby, you learn this. When you learn this, and then you combine it. So the most complicated things that I do for a living, okay, it's nothing more than just this. Okay, ability to put things into some kind of scale, translate that into mathematics, then using some mathematics that a bunch of other people invented long before I was born. Okay, and then get some result, project it back into reality. Okay, so that reality that you project back could be predicted temperature in the next 5 days. Right. So that's about number. Okay, so read that. That's a very good, I guess, philosophical thing. Now, first thing you do, what can you do with a number? Well, you can erase it. You can turn it negative. Okay, so you can do something to it. But I guess we might as well start with things like when you have two objects. Okay, now when you have two things, so first you have one thing. Now I have two things. Okay, completely abstract. I want you to try to start abstract. And again, you have no excuse to say, you came from a mathematics. You took calculus. You didn't take calculus. I'm not saying anything about calculus. Okay, you have two things. You have two things, right? A and B. Okay. Relation is describing A in reference to B or B in reference to A. It's a form of description. Okay. And we talk about measuring. So one of the most obvious thing is comparison, right? If you are 5 feet tall, the other one is 6 feet tall. This one is taller. Okay. So taller means nothing until you say taller than whom. A is taller than B. That makes sense. That's relationship. Okay. Relationship is a thing that you can say, and it could be true or false. Okay, just think of that. Okay, you relate A to B, and that relationship, it could be false. You can lie. Okay, you can say 5 is longer than 6. Okay, that's false. Okay, that's false. But certainly you can say it. Okay, but you're not producing anything. Okay, your output is sort of like a truth or false. Okay. Now, operation is different. Operation is like cooking. You take something, you add something, you get something else, right? You get coffee plus milk, you get latte or something. Okay, that's the meaning of operation. So binary relation, binary operation, this is the thing that you're going to play with, and we're going to play with very mechanical thing. Okay, so let's try something. Let's try something. Now, this is if you have, actually, you guys start the Mathematica, just a free, just just a new file. Start a new file. Okay. Okay. And now this is one of those things where I can, again, if it's like a presentation, a slide you take home, you read. It's. I want you to actually experience yourself. Just type in something like what I do now. Okay. 0. Well, you can do this. You can do something even simpler. Let me do the same thing as you. Okay. So let's say 6 Okay, it's greater than 5. Well, 6 is greater than 5. Now, once you type that in, by the way, you can't, if you enter, you just go to the next line. Okay. Now, this is the mechanics of the software. You have to shift enter to say that, yeah, I really want some response out of you. Okay. Tell me. Okay. Tell me. So how about 6 is greater than 6? Okay. Right. So it's producing something, but it's not producing in the sense that you're doing something with 6 and 6. It's just a comparison. So that's it, right? On the other hand, if you do something like 6 plus 6, enter, is 12. Okay. By the way, you guys mostly are Thai, right? I tell you what my teaching technique is. There's a word called ขี่ช้างจับตั๊กแตน. Any of you guys are not Thai, you're probably not familiar with this. Okay. ขี่ช้างจับตั๊กแตน means you overkill. You use this advanced technology of riding on an elephant to catch a little insect, a little bug. Okay. But I do that all the time. Because if you know how to ride an elephant well and catch a takkatan, you can ride an elephant and catch maybe a monkey or a lion or something. Okay. Now, this is what I mean by that. So I'm going to overcomplicate something simple. And I found this trick to be wonderful. If I overcomplicate things that are so simple, things that are complicated become very simple. It's kind of weird, but it's kind of magic. Anyway, try this. Okay. So this is 6 plus 6, right? Everybody's familiar with this. You can do that. Now, in Mathematica, the operation or the function use a square bracket. Okay. So if I do this, plus, okay, plus. Every Mathematica built-in start with a capital letter, okay, and no space. And notice if I type something silly, it's in blue, okay? Blue means something that's not defined yet. It's still, you know, free to be anything, okay? But things that are not free, like number 6, is black. So if I say plus, you notice it turns black because it's something that Mathematica already understands. It's, you know, you can't use it again. You can't redefine it, right? Certain thing you can redefine, but certainly it knows. So this becomes a function. I plus 4 and 5. Okay. Now, again, ขี่ช้างจับตั๊กแตน, right? I'm riding an elephant. Okay. You can add 4 to 5 in your head. But the point is now you realize you're not adding 4 and 5. You're actually doing something else. You are supplying, okay? Look at, pay attention to this. You are not adding 4 and 5. You have 4 and 5. You are supplying to a function that has room to put in rooms like a placeholder, right? Placeholder. This function is, okay, you can see this. This function is plus. It has 2 room. It takes something. I put comma in between because it has 2 spots. It's taking 2 spots. You are supplying 4 and 5 to a function that expects, in this case, 2 arguments. Okay, so the first word you supply is 5 and 4. Okay. Okay, and that becomes this. So in this case, this is not the fundamental. This is kind of like a shorthand now, right? It's like a shorthand. Well, I'm going to say, I'm going to take for granted that a lot of you are going to be following, you know, my track, Applied Digital Intelligence. In that world, you do a lot of plusing, but the meaning of plus will slightly different. Sometimes you're not adding length to length. Sometimes you're adding excess information. Okay. It's a little bit like if I add you and you, I don't actually have 2 heights. I actually have intelligence and media savviness, and you become a complete package. You know, it's one of those things like teamwork kind of thing. Well, that is a mathematical notion of plus, but in a more general form. So in the future, you can do something like my special plus, my special plusing. Okay, but you have to define that. Okay, you have to define that. So right away, you're not adding to number. You're not adding to number. You're supplying two arguments. Okay, the word is argument, like you argue. I don't know why it's called argument. It's kind of weird. You're supplying two arguments to a function that expects two arguments. Moreover, what else can you tell by this function? This function is completely symmetric with respect to the order. So if you put in +4, okay, and you say, is it equal to? Okay, this is the checking for equal. Equal twice plus 5 and 4. Can you do that? That's going to give you true, right? Let's give you true. Now, if I do this and I change it to something like exponential or something like that, or say power, okay, and then power. That's false, right? So order does matter, okay? So all this thing, you have to be mindful, and this is something that it's hard to tell you how important this kind of skill is. Okay, you go to a problem. Okay, my analogy would be you go to say I go to a consultancy project. Okay, I see A and B, and I know I need to do something to it. Immediately, I have to check to myself: does it matter if I get A before B or B before A? The operation matters. Okay, so power 4 to the 5 and 5 to the 4 is certainly not the same, right? So that's false. So again, this is too much. Anybody knows that. Okay, so you have to distinguish between operations that are symmetric or not symmetric. Okay, by the way, if you cook, it's the same thing, right? You beat an egg before you fry an egg and then before you beat. It certainly is a sequence. In that case, it's a sequence, not the argument. Okay, fine. So let's do that. So you can do equality. Okay, greater than, less than. Okay, this is easy, right? So greater than, equal. By the way, it's gonna do automatically the conversion. Okay, or it's true. Now, what if it's not true, right? Is it true? Is it true? Okay, it's true. So what if I do this and I put not in front of it? Nope, I'm not sure if that's a symbol. It becomes a false. So these are all logical operators. So I don't have to pay attention to too much. So anyway, so this is kind of example I want to say. Now, with logic, here's a logic, right? Here's a logic. You can do something like this. And, right? And means you're checking two things. Okay, and checking two things. So is 1 greater than 0.5 and 5 is greater than 4? True, right? And or that's also true. Now here's a funny thing. XOR. XOR means it's one thing has to be true, but not both. Okay. Okay. So it's one of those things. It's one of those things. So this has to be true, or this has to be true, but you can't have both true. So in this case, you happen to have the both true, so it's false. So it's XOR. And that happens a lot. Okay. Addition, subtraction, multiplication, division, blah, blah, blah. You know all this. You know all this. Okay. Now, in this case, now I'm running through this. Some of this is not, again, it is mathematical abstraction. Okay. Mathematics is a little bit like games. So it's solving your life problem. Before two mathematicians can play a game, they have to decide what games they're playing. Okay. And their games involve relation and operation. But they have to say something like, you know, today we're going to play this game where the operation is only symmetric. So you can only play with symmetric operation today. You can't, if you play with operation like exponential, you know, nobody talks to you. It's a wrong game. It's wrong game, right? It's wrong game. That, okay, the technical word for it is the assumption. Okay, mathematicians do this. Before they talk to each other, they agree. Today, we're going to talk about symmetric function, okay? If you want to talk about asymmetric function, you go somewhere else. It's not today. Today, A, some B is the same thing as B. It's called reflex. It's symmetric. When you do your project. Okay, it doesn't matter, you know, I don't want to waste time, but to be before A, you're doing drag trial. This is like this, things that seem, you know, like this. So like symmetry, asymmetry, okay? So symmetry, so relationship, reflexive, well, reflexive is some of this you would see in mathematical notebook, mathematical lessons in high school, whatever, you know, transitive relationship. If I like you and you like somebody else, then I also like that person. Okay? Is love transitive? Love not transitive, because I can love, but I really can't get along with the third person. Okay, so love is not transitive, but certainly height is. If I'm taller than this person taller than that person. Okay, right? So we're talking about here transitive. Okay, commutative. So these are, you know, property of, it's not that important. Now I'm going to start talking about function. Okay, now certainly we did this, right? You say we did. Okay, 4, 5, right? Now what if we do my, now here's the thing, okay? My special plus. Okay, now I don't want to talk about do it for 5 and 4, right? I want to do it for anybody. So I'm going to do it for, say, X, okay, and Y. Now there's now this thing you have to memorize, because it's a condition to tell Mathematica that this is something generic. Okay, you put an underscore here, so think of it as a variable. It's not a particular value. So I'm gonna do this. Okay. Now I'm going to make a definition of a function. So I'm not using it now, right? I'm going to tell you, okay, this is how I want it to do. It should do X plus Y. And then 0.1. I don't know. I just something weird. I just want to do something weird. Okay. I don't care. Okay. So I just define this. Okay? I just define this. Now you notice before that this was blue, right? Now it's black. You buy it. Okay. With 4 and 5, and you get 9.1. Okay. It's a special thing, right? Now, if I want to do something more complicated, okay, I can say something like it's one line, but it's certainly different, right? This is your own thing, right? I have another one. So now I'm going to do a few steps. Okay, a few steps. I don't, so this will be the same as before. Okay. Now I'm going to create my own thing. Okay. And but certainly I'm going to teach you how an elephant now. I'm going to make what's called a module. Right? Module means it's something that's close. Okay. So within that module, I can do something else. I can define something special. Okay. I can define something special. I can say, okay, the special is put in this curly. It's something special. And so there's two parts. Module is also a function. It requires two things. Okay. It requires certain definition, and certain action. In case my definition is that comes from outside. It's variable that's created when I use it. Okay, it's created. If you talk to your friends in programming, again, this is going to help ADI people more than the rest, but certainly value sum is going to be created when you use this function. Then I say temp, and this is my action. Temp equal to x plus y. X plus y here doesn't have to have underscore because we know now this x and y is the same thing. When you type in, you can notice all this variable will be in green, and it's sort of like kind of reflects. So if I type in something, it doesn't, right? But this it knows because it's something you just did, right? Now, next sentence is not used. You don't use full stop. So this is the only thing you need to remember. You use semicolon. Okay. And then temp is equal to temp plus 0.1. Oops. Okay. Now I'm just going to make it really, elaborate. Return. Okay. Okay. And now I finish my module. So now I do this same thing as before, but it's my special plus 2. Oop. I get 9.1. Okay. It's exact same before. Again, this is riding an elephant. Okay. Riding an elephant, right? Okay, fine. So that is basically how you start to build. Once you get into this kind of structure where you don't just do one step, you can do many steps, right? What happens now? You can start to build complication on complication. Okay, let me go to the next step. Let's just say I do this. My temp is equal to my special plus x and y first. Okay, and now I add 2. Okay, let's do this. What's going to happen? It's going to get 9.3, right? Right? Because this function call this function and then do something else to it. Okay. Now, why am I teaching you how to write an elephant? Because this writing an elephant is the basic structure of what's called functional programming. Okay, when you go to take Python class or R, or well, mostly I think in Basai you'll be learning Python. So now we have a interval scale, right? So I can say that today is 35 degree and global temperature. Remember that alpha, Wolfram alpha, global temperature, right? So the difference of 2 degrees between 35 and 37 and another 2 degrees to 39. So you can say that the gap, you can compare the gap, right? But what you cannot do, can you do this? Can you do this? Can you do this? You say today, right? today is 35 degrees centigrade. The temperature is 35 degrees centigrade. And this one is 70 degrees centigrade. Can you say that this is twice as hot? Because 70 divided by 35 is 2, right? Can you say that? Well, you can say that, you'd be wrong. Because there's no absolute zero. If I ask you the same question, but I use Fahrenheit, the numbers will be different, right? 35 will be 32 plus 35 times 9 divided by 5. And 70 would be 32 plus 70 multiplied by 9 divided by 5. And the division is going to be less than 2. Right? So you can't say that this is hotter than this, twice as hot. So there's no absolute zero. If there's no absolute zero, there's no absolute negative or positive. You can't do ratio. Okay? Finally, let's get to something where you can do ratio. Obviously, your height. You can have a zero height. Well, that's kind of silly, but certainly you can say this person is twice as tall as or 30% taller than the other person. It doesn't matter if I'm using metric or imperial. The number is the same, right? By the way, the temperature is only relevant if you don't work off of absolute zero, but you know, that's no idea. Okay, something else. Okay, so this is it. And so many supervised machine learning gets this thing wrong between the ordinal, interval, and ratio scale. Usually the nominal scale part, they don't get it wrong because it becomes something like a classification problem. When you get to prediction problem, they mix the 3 scales together and the interpretation can be completely silly. Okay, so that's why I make the emphasis on this. This is something that, you know, it's really should be like a second nature, but it isn't for some reason. Right. Okay, so we're working with the nitty-gritty. Again, today hopefully it's you know, it's as boring as it gets, but this is the basic, right? This is the wiring. This is the wiring. So you have object A and B. You can say something about A relative to B. That's relation, right? You can make something out of A and B. That's operation. Now, I talk about binary operation, but there are other operations that takes more than 2. Okay. In fact, the reason we use computer is because a lot of life situation in life, you deal with more than 2. You deal with 100, you deal with 1,000, you deal with a gazillion. Okay. You may do it 2 at a time. So if I'm adding 5,000 number, algorithmically, I might be adding 2 at a time. Okay, keep adding, keep adding, keep adding, keep adding, keep adding 1,000 times. But at the end of the day, mathematically, it's adding a whole bunch of them, right? And you don't want to do it by yourself. You want a computer to do it. So obviously, you got to start thinking about how are we going to think about things that comes in a whole bunch. That's where the concept of set comes in. Set comes in, okay? That's where concept of set. Set is like collection of things. That's it. Now, intuitively, and you will be right, intuitively, you would not put, say, set of things, and you say the first thing in a set is a phone, the second thing is you, the third thing is a dog, okay? That seems kind of like weird, right? To put things together that kind of like don't look like, but it's valid. It's completely valid, right? Because if I'm going to buy, say, transportation, okay? It doesn't matter. You will have different rate, but the rate for shipping this iPhone is cost money to ship this phone, cost money to send you to Ayutthaya or whatever, right? It also costs money to send a dog to Ayutthaya. So from that perspective, yeah, it's a set of things you can send and charge money for. Okay, but intuitively, you would think of set as something that has a common property. But I'm telling you, it only is a common property depending on what you want to do with it, right? So if I want to, I don't know, kill germs, I can use this. I can't do this. But if I want to ship FedEx or whatever, This thing costs money to ship to America. This thing costs money to ship to America too, right? This thing costs some money to insure. This one costs money to insure. This one has monetary value. This one has monetary value. Okay. So set is just a collection of objects. That's it. That's all. Now, if the set is a set of things, you can certainly count, right? How many things there are. And if you're talking about real life thing, it's finite. Okay. That number, how many students in a class, is called cardinality. Cardinality, okay? Gives the number of unique set members. Why don't they just use say how the number of things? Well, because set can be more abstract, and this is where power of mathematics come in. If I'm not talking about set of students, I'm talking about set of real number, set of prices that you can charge your customer. Okay. Certainly, it doesn't have to be something that finite, because let's say I open a store. This costs 5 baht. This costs 10 baht, right? So I have a set of 2. There's number 5, number 10. What's stopping me tomorrow from coming in tomorrow and selling another product and say, okay, this one is 750, right? There's absolutely no stopping me. And I can keep doing this infinitely. Okay. Well, when you have discrete element like this, and that's another word, discrete, 1, 2, 3, 4, 5, you can count them. Okay. There's a set called finite. That means number of students in this class. Okay. How about countably infinite or infinite? Sometimes you say that. That means it's discrete. You can count. It's countable, but it's not, you cannot stop. For example, set of integers. You can start counting now. 1, 2, 3, 4, 5. You can count. It's countable, but it's infinite. So you can't stop. Once you start, you can go to infinity. Okay. So that's the cardinality of that set is infinity. But it's a small infinity. And this is something weird, but don't have to pay attention to it. There's a big infinity and there's a small infinity. All right. The cardinality of a countable set is infinite, but it's a small infinite. On the other hand, set of real number between 0 and 1, just a very small interval, right? That is a huge possibility, because it doesn't matter what number you give me. I can always make a tiny number next to it. Okay. So it's bounded from 0 to 1, but it's infinite. Now this infinity is actually bigger than integer. Funny enough. Okay. And then you have semi-bounded. You have semi-bounded like positive number, right? From 0 to infinity, any number. Double bounded, 0 to 1. Okay. Or unbounded, minus infinity to plus infinity. That's it. Right. And then once you have set, then you have things like set operation. Okay. I want a complement of a boy, girls, right? Intersection. Okay. Boys and people with glasses. Okay. Then I intersect, I get boys with glasses. Union. All right. Symmetric difference. That's the same thing like XOR. Boy or glasses, but not both. Okay, so that's symmetric difference. This is akin to XOR. Power set and sigma algebra, I'm not going to talk about it because that's a little bit, well, it's a little bit much. But the power set you can certainly do. If I have a group of 5 students, okay, how many ways can I pick a team? I can pick all 5. I can pick 4, but there are actually 5 versions of 4 by excluding different person, right? And I can also pick 3, but there are more than just any 3. It's called 5 choose 3 combination. Technically, it's 5 factorial divided by 2 factorial times 3 factorial, but okay. Basically, if I 5 of you, I can pick any team. I can pick 5. I can pick 4, and there are 5 versions of that. I can pick 3, and I can pick 2, and pick 1. I can pick 0. The set of set is called power set, and this becomes critical when you deal with data combination clients. You know, if you think about, let's say you're making a product and you sort of like, you know, trying to see kind of subsetting different combination of clients and so forth, that would be something that would come up, but you know, not much. Sigma algebra is something else. I'll skip that. And then you have logic, right? Logic is and or, and usually you have this thing like true, false, and so some of these things you can go through yourself, certainly. Okay. Now, let's get active. These are all the basic wires. In a robotic labs, you have to work with wires, you have to work with boxes and plastic. This is it. This is it. This is all there is. Okay. Once you get to, say, data analytics or applied digital intelligence or machine learning, we'll generalize concept of things you can play with in a computer from those numbers. But now that's it. Let's just say this is all you have, just some numbers. Okay. Just represent it as A or B or X or Y. Okay. And you have collection of them. Okay. So you have numbers, set of numbers. That's all you can play with. That's all the object. Now you're going to play with them. Okay. Now you're going to play with them. The key thing that you use to play with is equation. Where are we? Okay, good. Equation. Equation is like the syntax, right? When you speak a language, if I teach you a new language, what do you have to do? You have to learn about vocabulary, right? Vocabularies. But can you get by with vocabulary if you don't have grammar, right? I eat cat, cat eats me, or, you know, I kick dog, dog kick I, right? It means different thing, right? Okay. So it's not enough to know the thing. You have to know some kind of syntax. The main syntax in mathematics, okay, and this is where it differs a little bit between mathematics and programming. The syntax in mathematics is usually a one-shot deal. And that the main link, the main action verb in the sentence is the equality sign. Left-hand side equal to right-hand side. Okay. But when mathematics does that, it means you are saying, okay, you're saying A equals to B. In programming, it's slightly different. You can be checking whether or not A is equal to B. You can say that A is equal to B, but it hasn't equal to B before because A used to equal to C. And now I'm making an assignment. You can say my special plus is equal to this operation. You can say my cooking recipe equal to 10 different steps to get from eggs and chicken, raw eggs and chicken to finished dinner. Okay, so in mathematics, it's usually a one-shot deal. A is equal to B, right? But in programming, equality is kind of assignment, a whole bunch of steps. So you can assign A equal to procedure. Okay, so that's a little different between the two sense. But equality. Okay, so that's why in Mathematica, you know, A equal to 3. Okay, this is okay. This is valid. This is called assignment. Okay, so this is assignment. Once you make an assignment, A is equal to 5. It is true. You're checking, right? So you can also do this. Is 5 equal to 6? False. But what you cannot do is 5 equal to 6 because you cannot assign 6 to 5. right? 5 is not a name. Okay, 5 is not a name. So this equation, this is, I guess to distinguish two cases, we would say this is equality relation, checking if it's equal. This is assignment. Okay. Now, when you see something in mathematics that say the left-hand side, right-hand side, okay, you can assume from the context that, you know, it's a truth. It's a truth. Okay. In computing, you can check. It becomes a matter of checking. Is it equal? Okay, but if you see something written on a piece of paper, you know, GDP of Thailand is growth is, you know, 7.4%, then you don't say, is it true? You just take it as truth, right? So that's what equation is. But so the key things that you'll be working with in Mathematica, in your analysis, is equation. Right? This is how you link one truth to the other. Okay. And this is very important. This is kind of like a scientific reference. You know, when I say that you are 5 feet tall, implicitly, I'm speaking to someone who does know what 5 feet is, but doesn't know how tall you are. Right? The information I impart in that sentence is to say that you don't know how tall. I talked to another person, right? He doesn't know how tall you are, but he knows what 5 feet is. So I say, you are 5 feet tall. Your height equal to 5 feet. The truth of the number 5 feet is transferred to your height. That becomes information. Okay, so that's the information flow, and it always goes to the right to left. That's a convention. You write left to right, but information goes from right to left. You are how much? How tall are you? You are equal to the right-hand side. Information goes from the right-hand side to the left-hand side. Okay? Right. There's function. Now, this is where it gets tricky. Okay, function. If I want to define this function, my special, I did this, right? Let's do this. My special plus is equal to this. Okay? This is that. But it's so short. I don't want to name it. And this is a shorthand that becomes, again, I'm benefiting the applied digital intelligence people a bit more, because this is something that's very efficient in data science. But I'll show it now. Okay. This is what I want to do. Okay. If I want to do it all the time, I can define this function. Okay. But if I want to just do it once, okay, I can just tell the action. Okay. I want to take the first guy, add the second guy. Okay. And 0.1. And I add this ampersand. Now, this is going to be something very efficient for data scientists. So, you know, but the rest of you can pay attention to. By putting ampersand, it's saying it's called a pure function. It's a function that doesn't have a name. Okay. So instead of saying, remember I said, I want you to reach out and touch your friend's shoulder, right? Before I do that, I have to define a function, touching shoulder. And I say, touching shoulder, open bracket, you, comma, you, right? But touching shoulder is just a one-time function I don't want to use, okay? So what I'm going to do is to say, hey, look at this. Hey, look at this. This thing, touch this thing. Now you do it. It's like monkey see, monkey do kind of thing, okay? So this thing does this, and apply it to 3 and 4. Okay, so this is kind of like monkey see, monkey do kind of thing, right? So I don't have to name this function. I don't have to name this function. I just do it once. This becomes, for data scientists, extremely powerful. And in Python, this would be called pure function, like, ampersand function, yeah? Lambda function, sorry. Sorry. In Python, it's called lambda. So pure function is extremely useful because sometimes you want tiny filtering to go through the whole data set, right? And you just want to stick this particular thing. For example, for this data set, for some weird reason, I asked for centigrade, Celsius, and they give me something in Fahrenheit, right? But I don't want to build a conversion. So all I do is just create a number and say something like, take this number. Now, I just have one number, so I don't have to say 1 and 2, okay? This thing, multiply by 5 and divide by 9 and add 32, okay? And now this thing would work for every time I see a centigrade, sorry, Fahrenheit, okay? So your friends say, it is 68 degrees today. It's that, okay? Now, Mathematica is a little bit, it's a side comment. Mathematica wants to be pure. So this is the correct answer. It's not going to give you decimal answer unless you force it to, because this is more precise. So if you want to force it to, you put number, n. Big N is a reserved word for saying, give me a numerical, okay? So if somebody say, oh, today is so hot, it's 98 degrees. Oh, it's 86 degrees or whatever. Oh, sorry, subtract, right? No wonder the number looks funny. Okay. Okay. Right. Is that right? Yeah, I think so. Okay. So this is called a pure function. Okay. I'm not going to say any more about it because most of the time you will write a name function. Okay. So in Mathematica, there are 3 kinds of function. Okay. Well, name function. One, universal function like addition. All right. It doesn't matter what program you do, it's going to have that function. It's called, well, universal function, right? Like plus or minus or exponential. These are pure mathematics. Any program must be able to do that. Like a calculator, you can't buy a calculator that doesn't have a subtraction button, for example, right? So this is universal. The other things are called built-in function. This is what gives Mathematica the power to analyze your data. Okay, it's a procedure that somebody before you program. So they did something like my special plus, but it's general enough that you use it all the time. So that's why in before today we'll go over some of these. So these are called built-in. Okay, this is called built-in, and then finally there's user-defined. So there's universal mathematics, there's built-in function, and this built-in function gets bigger and bigger every year. Okay, every version of Mathematica, you have more power. Okay, it has more, because if you think about it, things like looking at a cat and say it's a cat, it's an AI function. 20 years ago, you didn't have an efficient algorithm for this. So it wasn't built in. Okay, but now it's built in. You can say classify or identify, and you show a picture of cat, it's going to say cat. Okay, so a lot more things get built in, get more built in. Now with Python, it's different. Python doesn't have built in, so you have to keep loading library, what's called libraries. So libraries are libraries of function. If you want to do this set of functionality, you have to load this library, and then you have to load more library for this, for that, for that, for that. So it's not comprehensive, but it's more flexible because you can work in different areas. For example, I have my own research project with your TA here that looks into what's called Vine copula. It's a mathematical model for figuring out relationship between financial variables. Well, this is a special technique that only few people understand it or use it. It's written not in Python, but it's written in R. So I start R, but before I use it, I have to load this library. Okay. Well, Mathematica is not like that. Mathematica is either built in or you write your own define. Okay. So you can build your own library, but they don't have that kind of thing. So you can share, but you can have open source community as well if you like. Right. Now, I want to show, okay, I want to show that with, okay, this case, right? This is not good. I showed you a little bit about manipulate last time, so I'm not going to do that, but a lot of things, and this is going to be useful for everyone here, is the visualization of data. If you're not going to be a data scientist, you might not work with a huge, big gigabytes of data, but you certainly will be working with some kind of information, right? Some kind of dimension, some kind of market result. What's your, what are you trying to sell your product to? What's an average age of your clients and so forth and all. So you're going to be working with data. So what I want you to do is, let me go to this. Well, first of all, let's go to this page. This page is called reference.wolfram.com. Wolfram is the last name of the person who invented Mathematica. So put his last name on it. Okay. Reference.wolfram.com. So that's that. And this has all kinds of stuff. So data manipulation, visualization. Now, it's going to look like this, right? It's going to look like this. The bottom here is about deployment. It's like you are at the end of your senior project, right? Capstone or whatever you call it. And you want to literally prototype your product. This is where things come in handy. Okay. So this is far end. This is sort of like you've done your analysis. You're ready to sort of like pitch to an investor, right? This is where things come in. Okay. The documentation, the interface, deployment, like I show you, you can use it in cloud and stuff. So these are the last, the functionality that has to do with that. So I'm not going to cover that here. Okay. Come up a little bit more. It's more apply, but doesn't get quite to deployment state. So these are special function that sort of like separate by discipline. Now, because you guys are BASI, you're not single discipline, you're multidiscipline, right? So one day you might be looking at medical data or trying to work with medical information, medical informatics, right? Next thing you might want to say, well, I want to sort of like create an overlay with the population, visualize of different region of Thailand or something, geographic data. So that's here, right? Time related computation, that'd be like time series and all kind of stuff. Engineering. So, and if you want to work in financial data, I mean, I spend most of my career in finance anyway. So I look into something like this. So these are more kind of like disciplinary kind of grouping. Okay. So I'm going backward from simple to complex. Now, when you go to here, this is where I talked about this generalization from numbers to something that has to be translated to numbers. Strings and text, like Hamlet's, your poetry, words, okay? Geometry. This means literally you can represent mathematically what a triangle, what this and that. So sound, video, you can do sound processing. I don't know if some of you are in a band, or some of you are in digital photography, right? You can take your picture and you can process it in here. That's image. So this is about, to use a modern language, it's called big data. It's a variety of data. Okay, so this is not domain specific. It's not engineering. It's not finance. But in finance or engineering, sometimes you have image. Right? You have image in engineering, you have image in science, you have image in medical data, right? So it's more generic, but it's still sort of like generalization of what it means to work with an object. An object, that's an information, it doesn't come into numbers, but you have to do something with it to make it numbers, and you have to be able to work with it, right? And then these are the basic. So core language, this is the boring stuff that I'm telling you today, right? Core language, like how to put open bracket, how to close bracket, how to put module. So these are the thing that, again, is the most boring, but if you can't splice a wire, you can't do robotic labs. Okay. Data manipulation, this is very general. Visualization, symbolic, this would means things like this is something, by the way, that you can do in mathematics that things like Python would never able to do. It can literally solve equation for you, not numerically, logically. You know, like when you're in high school, I don't know if you, some of you in high school, you say something like, you know, x squared minus 3x plus 2, right? You have to factor out. Okay. Python can't do that. But you can actually do this. You can ask Mathematica to, so it's a very human logic kind of thing called simplify or factor or something like that. Simplify or factor, okay? So you can actually do logic, okay? You can take calculus derivative. Now, we'll talk about it later. And again, because this is about interactive, the exercise would not be for you to do it by hand, but to use Mathematica. So just to give you a preview, right? Let's say I have a function, right? I have a function. My function is x squared plus 4x minus log of x. Okay, so this is my function, right? Now, this symbolic thing here means I can do this. Okay, take the derivative of this with respect to this. Okay. Yeah, this is calculus, guys. That's it. It just did calculus for you. Okay. And the ability to do this is so amazing. Now, with most programs like Python or C, what you have to do is numerically. It can't do this logically. You can only do it for a particular value. So if I add, let's say I set x is equal to 5, then it can do that numerically. But if I just say, give me a general formula, I have actually used this in my own career. Okay, when I was at Siam Commercial Bank, they were trying to trade what's called exotic derivatives, you know, some FX derivative, and it has certain models and it requires differentiation. And to do this by hand or in a spreadsheet, forget it. It would take forever. Okay, so I've actually used this professionally. Okay, so anyway, so this is analytical. This is symbolic. Okay, this is something that is not, it's not just numerical. But again, this, by the way, if you ask me what is the one thing that cannot be done anywhere else, it's this block here. Okay, you can do a lot of sound video editing with C, C++, Java, and all kind of stuff. But this thing here, okay, but I'm not going to talk too much about it. Same here, mathematical computation. These two things are what sets it apart. But from your perspective, what sets it apart is the high levelness. Okay, so the high level would be, and today I'm just going to give you one example, visualization. Okay, now visualization has many ways. I'm just going to show you one thing that I literally used for I think my son's high school project or something was doing something like radial axis plot. Okay, so this was his paper. Okay, just download. This was my any of you went to Triam Udom? No? Triam Udom here? No? Down the street? No? No, nobody came from Triam Udom? No? Okay, sorry. Anyway, my kid, my son was doing some kind of project, and so download the data here, okay, from our world in data, and then did some kind of analysis. But the key thing, I think the nicest one I think I saw was this. It's kind of like a radar plot. This is a visualization. For example, different country like Asia, right? So what it's looking at is a group of country. Asia is a group of country. The thickness represents, I think, population, if I'm not mistaken. Okay, it's not. Okay, just give an example. I think that's the thickness is population. Yeah, because Asia is bigger, right? And then Europe, Africa, Oceania. Now these are various metric, cases per millions. I don't know if you know, hour in data or odometer that you look at the COVID, right? So this is download the time series and looking at it from cross-country perspective. So GDP per capita, Human Development Index, proportion, age, you know. So you can see that Asia really high population density, but case per million is not so high compared to Europe. Okay, Europe is has very high case per millions, has very low diabetes. I guess that's funny. Oceania, they have low case. Oceania is very good. They're good in everything except diabetes. Okay, they're very big. They like to eat sugar, and this is historical because Oceania people instinctively they have to eat a lot of carb, store a lot of fat, because sometimes they go from one island to the other. They don't know when they're going to hit land. Okay, so their ideas of beauty is fat and huge and big. So nowadays you don't have to worry about getting lost on an island. So they continue to eat a lot, so they get diabetes. Okay, so this is kind of like a radar plot. This is kind of like clustering. You want to know about it into, you know, data science, and this is identifying Thailand, and that's a little bit of a benchmark. Like if you did a straight line spread, is Thailand better than average? Okay, something like that. I think this was done a while back. This yes, my kid is no longer in high school, but this was when he was in high school. So the point is, yeah, uses this, right? This is manipulate screen that you saw the other day. Okay, except here it would be choice of countries to display. Okay, so you can do this. You can do all kind of you know, forget about making PowerPoint presentation. You should be making Mathematica presentation with live data, or at least with configurable data. Okay, so that's, I think, yeah, this was a while back, wasn't it? Because if you remember correctly, I think the curve would be a little bit here by now, I think, right? It's much less. Okay, so anyway, this is doing visualization. This is just using just one thing, this thing called radial axis plot. Okay, but you can do other things like stack list plot and all kind of stuff. Okay, and the nice thing is it does a lot of 3D. Oh, this is another example. I'll show you one picture that it's in an ongoing project that I'm literally doing. Okay, so this is actually, this represents companies in Thailand. Every single company in Thailand is in here somewhere. Okay, and the clustering is an indication of when two companies are connected by, I think, directorship. Okay, you know, like in companies you have a board of director, right? Well, board of director in Thailand is kind of like a small pool of people for some reason. So if I sit on one board, chances are I sit on other board and so forth. So this is saying the board is related to a company, a board is related to a company. I'm going to link two companies if they share the same board. Okay, and there are some companies that don't share boards. So these are kind of like small, but there's a huge cluster in Thailand of companies, you know, all the set listed companies that are linked. Okay, so this is a visualization that I actually use this for my current project. Well, it's based on something like this. Okay, like graph plot or community graph plot. You can do in 3D, 2D, whatever. Okay, so social network analysis, for example, is based on this functionalities. Hold on, let me show you. So let me go back to here. Okay, the mathematics is here, the graph and the network. Okay, this is how you model how close a person is to another person by connectivity, by links, by likes, by sharing Netflix download. Okay, so the mathematics is done here, but the visualization is here. Okay. So that's that. So let me go back to the, see what I need to cover. Okay, so again, I'm just making a case that you can redefine addition. Okay, so we did this already. Subtract, divide, blah, 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 exponential. Okay. Now, this is an example. Okay. Now, there are many built-in functions. But what I'm going to do is, I think by the end of this summer, I might sort of like shortlist for you, say 20 most useful list, most useful function. Okay. Well, you already saw one. Manipulate is one. Okay, manipulate is one. Manipulate allows you to play with parameters and visualize and all that stuff. It's automated for you. You don't have to draw. You know, when I was doing my PhD, I did my algorithmic trading software. I was writing it in C++. I actually have to create a window and have to say, you know, goes from this end to that end, so many pixels, so many spots, and so forth. It took forever. Took me forever, you know, to doing some kind of visualization. Now you just type in manipulate and everything is automated. Okay. Now, if you're finicky, you want to fine tune the size, you can do that. Okay. But the point is, at a high level, it's automatic. Okay. And that's what I mean by I want you to go to this thing, right? Demonstration, and see if you can copy the homework. Okay. By the way, you've done that, right? You go to this. Every time you download, you go to download and go to the authors page, right? And I say, okay, this is what they display. You want to copy their homework. Okay, what you do, you just double click here. And that's the code. That's the code. Okay, now, obviously, your problem will be different, right? So you would copy it. What you would do this. You just copy this and go to new notebook. Okay, do that, right? So now it's your thing, but you don't want this function. You want some other function. So maybe I'll just do something like, I don't know. Okay, it'll come to something else. Okay, so you can copy that, see, and everything is there. All the manipulation of B1, B2, B3, blah, blah, blah. I can make this, I can make that. Okay. By the way, the reason I have this example, anybody knows, anybody has a friend in engineering? Okay, well, if you have a friend in engineering, when they get to sophomore, that's next year, they're going to learn about partial differential equation in many different things. Maybe even this year, in freshman year. The point is, this represents, let me go back to original. This represents temperature. So if I have a heat abroad, right? And I have heat, this is how hot it is. Okay, this is how hot it is. And over time, it cools down. Okay. And the solution to this is mathematics. Okay. Now, why do I show you this picture? This is a segue to talk about multidisciplinary innovation. This mathematics has been around for hundreds of years. It's called heat equation. Okay. It says that if you have something that's hot, how would the temperature change? The key element is that the reason the temperature change is if there's a sharp difference between your neighbor. Think of it this way. If you're hot-headed and your friend's hot-headed, your friend is hot-headed, you don't cool down, right? Right? So your temperature doesn't change. If you're hot-headed, but you are very nice and calm, you calm down quickly, right? Right? Okay. your hot-headedness is a function of time. Okay? But the difference in hot-headedness is a function of your neighbor. The more difference you are with your neighbor, the faster you lose your heat. Likewise, if your friend is hot-headed, this friend is hot-headed, and you're cool, you're not going to stay calm very long because you're going to become hot-headed like your friend. Okay? So this is what? Engineering, right? Thermodynamics. Guys, done. Okay? So this is heat equation. This has been around for a while. It's called partial differential equation. Would you believe me if I say this equation won 3 guys Nobel Prize in economics for coming up with the formula for pricing derivative? Why? Because, and I'll show you, I just show you briefly, by the way. Oops. Okay, watch this. There. Okay. Well, this is something I, wrote when I was very young at Bank of Thailand. But the point is, the derivative formula try to link the price of option to the price of underlying stock. Okay. You don't have to worry about this, but let's say underlying price of stock is the price of something. Derivative is the right to buy something at a certain price. So if I can buy a stock in the future at 50 baht per share, okay, you can think of Bitcoin if you like, that's your thing, right? 50 baht per share is my right. So if it gets to that day and it's 40 baht, I get nothing. But if on that day, the thing rises in price to 70, I actually have free money worth what? 20, right? Because I can buy 50 and sell it at 70. That's called financial derivative. Well, it turns out that somebody, okay, I have an underlying price of stock. Okay, the stock can go up, the stock go down. Today, I buy an option price. That gives me the right to buy a particular stock at 50 baht per share. Come to that day, it rises. So basically, I benefit from the upside, but I don't suffer from the downside because I don't own the stock. So if it goes down, I just don't bother, right? So this is a kind of a non-linearity. Okay, you can apply this to stock, you can apply this to Bitcoin, you can apply this to durian, I don't care. Okay, the point is, through a series, somebody who I think started out as physics, in physics, started to study economic problem, look at this problem, realize that through certain argument, you can kind of like, even though the stock is up and down, it's called risky, goes up and down. You can actually precisely evaluate the derivative price without uncertainty. And through arguments, the solution is a problem. And that problem is this equation. Okay, that problem is this equation. There, okay? Here's the thing, and this is what I mean by transdisciplinary education. This equation is based on a problem in economics and finance. It was thought up by a physicist. But once he gets to this, he realizes, okay, you don't have to worry about any of this, okay? It's some kind of calculus. This is derivative of C with respect to T. And this is derivative, second derivative of C with respect to S. Now, T is time. T is time. C is the derivative that I want to price. S is the underlying stock. Okay, it looks like this, right? Now, what if I tell you T is T, but C is your hot-headedness as a function of time, and S is sort of like how that hot-headedness separate around your peers. So the more difference as measured by the second derivative your heat is relative to your friend, the cooler you get, the quicker you calm down, right? So if you're hot-headed, nobody changes the mood. If you calm, nobody changes mood. But if there's a high divergence, you're hot-headed, but around you are calm, you calm down. If you're cool, around you, everybody's hot-headed, you become hot-headed, right? Same thing here. Realizing that this is exactly the same equation as a heat equation here. These guys just walk to a undergraduate student in engineering. Well, he probably did it himself, but you know, theoretically, this could have been solved by undergraduate. The solution to that didn't win the students anything because it was pre-solved problem, but the insight of a physicist who looks at the problems, the economics and finance, formulate the argument, ends up with an equation that looks like something that mechanical engineer study in the first year, solve it, got them Nobel Prize. Okay. And you know, the long arc of this story is even longer. It goes all the way back to Einstein, who, anyway, in my I guess lifelong innovation class, I talked about that. The history of this Nobel Prize traced all the way back to botanists in the 18th century or 19th century. But anyway, it's a long arc. But the point is, the most recent cross-fertilization of idea, and that's why you guys are here. Okay, that cross-fertilization idea happened when you take a physicist and somehow maybe he didn't do very well in physics research. He started looking at problem in economics. Okay, and became, you know, and I'm being facetious here. If he stayed in physics, he probably wouldn't win any Nobel Prize. Okay, right. So that's it. So that this is an example, but this is so this is the useful function in Mathematica called manipulate. Okay, that's a manipulate function, right? Okay, so you already saw the first one that's extremely useful, that's manipulate function. The second one is called table. Table is to create a list. Remember I told you that you have list of students, right? But what if I have, I want to create a list of something. Say, I'm just gonna make a, let's make a new one. Let's go here. Table, okay? And this is how you do it. Okay, so type, experiment with this, okay? So let's say table of I square. Now, let's say I, okay? How do you do the superscript? Shift and, you know, the Chinese hat, the Vietnamese hat. Where is it? Okay, control, not shift, sorry. Control, Chinese hat, and say 5, okay? Now, this function expect two things. One is the action. It's kind of opposite of module. Module say what variable you want to play with here, and then what action. This is what action, and then it tells you the range. So I to 10, I to 10. So you can start if you do this. Okay, right? So it starts to iterate. Some of you will take Python class. This will be similar to what's called list comprehension, but it's about a bit more clumsy in Python. Here it's just a table. Okay, so what I want to do, I want to create a list of something to the power 5. And that something goes from 1 to 10. Now, okay, that's it. Now, if I want to go from, so by default, it goes from 1. But if you want to go from 5, you just put 5 first. So this is kind of like syntax, right? So what the way the syntax is written is the most common sense is the shortest way, right? So the shortest way is to do this. Well, what does it mean? Well, probably going from 1 to 10. But if you want to be more particular, more finicky, you can specify, okay, from 5 to 10. Okay, from say 4 to 10. Okay. Now, what if you don't want to go 4, 5, 6, 7, 8, 9, 10? You want to go to from 4 to 10 instead of 2. See that? Right? So again, this is not what makes Mathematica powerful. The Mathematica is powerful because of the symbolic ability, but this is what makes Mathematica easy to use, because it's trying to say the most common sense. You know, what you want to do, you know, a list of 10 things. Well, you start with 1, I guess, right? That's kind of common sense. It's kind of common sense. It doesn't have to be programmed this way, but it's written this way to correspond to the way a data scientist, well, the physicist, data scientist, mathematician thinks, right? So usually you iterate from 1 to 10. So why write 1? Forget it. Just write 10. Okay. But if you want more details, you say that. Okay. So this is it. Okay. And you can do anything like this. So table is one of the most useful. Okay. So now we got what? We got table. We got manipulate. Okay. By the end of this summer, or 2 weeks time, 3 weeks maybe at most, maybe there'll be like 20 that would last you not a lifetime. There's going to be a lot of plot. Okay, there's a lot of plotting. Okay, so radial axis plot is a version of plot, but there's some simpler form of plot. So, you know, you get a lot of mileage out of these guys. Okay, this thing allows you to visualize data. This thing allows you to create lists of data, even if you like, right? Manipulate allows you to visualize function, changing the parameter and so forth. So this thing will last you a lifetime. Okay, last you a lifetime. Okay. Now, so that's those are the basic tools. Those are the basic call it. Okay. So again, this a special kind of plot when you work with, but you get the point. Okay. Graph visual. Now, when you go from this page, from reference page, they're not going to take you immediately to the function definition, but usually to some kind of exposition. Okay, but when you click to individual one, that's when you get to function. All this clickable thing, graph plot. Okay, in fact, this thing that you saw I showed you earlier is done using graph plot 3D, 3-dimensional plot. Okay. So graph plot, you go to graph plot, and then you go to maybe graph plot. By the way, once you get to this, you can say reference language, and I can say 3D, right? Okay, so that's basically what I use for my project. So you know, so this thing literally makes me money. Okay, and I use this, by the way, in 2 projects, not just one. One project is about relating different companies in Thailand. The other one is about linking different financial markets. So this is on, you guys know what the SET market, right? Well, SET is Stock Exchange of Thailand. Okay. Well, they have a research sponsoring kind of thing. So allow professional to study the dynamics of financial market. Okay, so I was commissioned to do a project based on this. And the idea is not to link company to company, but to link financial market to financial market. Like, how is the SET market related to emerging market bond or S&P 500? Okay, now the same exact mechanism can be used to study relationship between, I don't know, Facebook friends. I don't, you know, I'm quite into this graph theory, by the way. I tell you why. Because when I was in Bank of Thailand, I was probably, and I can pretty sure claim this, I was the first person in Thailand to use eigenvector centrality analysis. But I didn't do it for Facebook. That wasn't my thing. I didn't care about Facebook. I still don't care about Facebook. But centrality analysis in social network. Long before it was a thing, about 5 years before it was a thing, I applied exactly same technique for connection, not between Facebook friends, but between financial institutions, banks. I was working for the Bank of Thailand. Okay. So the idea was I was working for the Bank of Thailand, and we wanted to know which bank is systemically important. Sometimes it's not the size, but it's the network effect. So I'm pretty sure I was probably the first guy in Thailand who used eigenvector centrality for the job. Okay. And 5 or 10 years later, Facebook became a thing, and then network centrality. So now you can actually go to like an online app to say, you know, who's your friend, and among the group of Facebook friend, who's the most eigencentral, or who's the most betweenness central, and so forth. Now it's very generic. Now it's very easy. Okay. But anyway, this is the visualization. The analysis would not be here. The analysis would be in this thing, graph and network. Okay. Graph distance, shortest path, find click, friends, who's connected to whom, right? This is all done algorithmically, but because it's become so commonplace. Okay. The earlier version of Mathematica, certainly when I was at the Bank of Thailand, Mathematica probably didn't have this kind of functionalities, not that I was aware of, but now it's become more common. So they keep wrapping. So now the library of Mathematica is huge. Okay. That's why it includes all the machine learning stuff. And that's the bit here. But I'm not going to talk too much about that, because a lot of you will be taking a data science track, and that's where machine learning comes into play. Okay. And this thing has so many built in. Okay. When I was not your age, when I was doing my PhD, you have to program neural network using, say, C language. Nowadays, you can literally say, build a neural network based on this data. Just one line. Okay. Something like, say, I don't know, I can't quite see, but so something like classify, or something like image classify, or predict. Yeah, that is. So I can literally do this. It's now built-in. Now it's a built-in function. You know, you can classify cats and dogs and whatnot, and you can train the model. So you have two things. You have built-in neural network that hasn't been trained. So you supply your own pictures. Okay. So so there's a built-in function here. Okay. That builds a neural network, but you want it to identify your friend. So you take all your friends' picture and you label this one's name, this and that, and you train the neural network. The neural network will learn to recognize your friend. But you also have generic learning problem like cats and dogs, right? Those things you don't have to supply your own data. It's already been done. And that's inside what's called model repository, Mathematica. Model repository. Yeah. Neural net repository. All the clever things, convolutional neural network, things that are built into your iPhone, all these are kind of in here. AlexNet, all these famous models are here. Okay. Now, obviously, the less famous or the more recent, the model that just came last month would not be here. That's why if you're a professional data scientist, Mathematica is not enough, because you can't afford to wait for update. So if something came last month, you might have to go to paper with code or something like that. Okay. And this thing came in 27th of June, 2022, right? If you happen to use this model, you can't use it in Mathematica, because, you know, unless it becomes ubiquitous, it would not be in the upgrade. Okay. So this is where I think things like Python are more professional, because it's more updated to the community effect. Okay. It's you know about this, right? This kind of shareware Just like you can share, if you know how to make something in 3D printing, you put it up in the library, somebody can download it and make it themselves, right? It's that open source feeling that Python is better. Right. Oh, sorry, I ran a little bit out of time, but the mechanic. So understand that at the end of the day, and you just have to take my word for it, any kind of analysis, any job you do involve analysis. Any analysis you do involve mathematics. Any mathematics you do involve turning real world object into numerical or abstract representation. Okay. And today, all we just learned is just the very basic nitty-gritty of what do you do when you have two numbers. You can compare them. You can say something about them. That's relationship. You can make something out of them. That's operation. You can create a whole bunch of them and refer to them as a list. So you don't refer to just you. I just say my students, and that's all of you, right? And then you can do some kind of set operation. You can do this, but ultimately, you don't want to do this by hand. So the mathematics that you have to understand how it's done, you will not have to do it yourself. Just do it with the function call. And Mathematica has allowed you to do that because all the mathematics universal functions are there, exponential, blah, blah, logs, everything. All the convenient ones are built over time, many years, many versions. And then still you get to something you want to do just for yourself, right? So there's a generic formula for making an omelet. You want your own special omelet. You write your own. That's called user-defined function. And that's how you communicate with your computer. Okay, this is called functional programming paradigm. So it's almost like I'm trying to teach you functional programming by showing you mathematical example, or I'm trying to teach you mathematics using functional programming. I'm not sure, which perspective applies here, but that's that. So again, it should, next time we'll go, like I told you that eventually you're going to have to touch linear algebra and calculus, and I'll show you what object and what operation comes in under those headings. Okay. And guarantee you that by the end of this summer, it doesn't matter if you didn't take calculus before. You should have the same intuition as your friends who took calculus and linear algebra. Okay, Kap, be punctual, come on time, and I'll see you next. Okay, Friday. Okay, Kap, see you. สวัสดีค่ะสวัสดีลูกเหรอ